Video is on magnitude comparator. Initially, let us start with an n-bit comparator. Let us see how it works. In an n-bit comparator, if a and b are the two inputs, each of n bit, let us say that from the n-bit comparator, we need to identify if a is greater than b, or if a is equal to b, or if a is less than b. So in these we need to identify and compare, and we have to show whether uh, the comparator is working for the logic circuits. Let us start with an 1-bit magnitude comparator. So for a 1-bit magnitude comparator, if you consider A and B are the two inputs, for the two inputs the various combinations are 4. It is 0 0 0 1 1 0 and 1 1. Let us see here, if A and B are of equal, your output for A equal to B should be 1, is it? And if it is not so, the remaining A less than B and A greater than B should be equal to 0. And in this case, next 0 and 1, if you see, if here in this case A is 0 and B is 1, which meant that A is less than B. Hence A is less than B should give an output as 1 and remaining 2 should be given as 0 0. Similarly, if A is equal to 1 and B is equal to 0, it is A greater than B. Is it? And if A and B are 1 1, see here A equal to B is equal to 1, the remaining 2 bits, that is the remaining outputs A less than B and A greater than B should be equal to 0. Keeping this in truth table, we need to identify the logic equation from this. See, starting from A greater than B, if you identify, you are getting 1 in this case where A is 1 and B is 0, is it? Hence we are directly writing it as AB bar. See, A is 1 and B is 0, hence we are writing AB bar. And another case, remaining all the bits for A greater than B is 0. See, remaining all the case for A greater than B is 0, hence it is not considered. And if you see A less than B, see here A bar B it is, and that is what it is given here. And if you see here A is equal to B, for two cases we are getting output 1. One is A bar B bar, another one is AB. For these two cases we are getting A is equal to B, and hence this is exclusive NOR equation, is it? That is what we are framing in this diagram, in the logic diagram. If you see here A and B, here it is A bar, is it? Here it is A bar, and here it is B bar, and here it is B bar. Okay, this is B, sorry, this is A actually, this is A and this is B. See, for A greater than B, AB bar, is it? A greater than B, it is AB bar, and here it is an inversion, hence it is A bar B to the whole bar, both are same, is it? Because once again we are making an inversion of the output, hence we will get both as in same output. Similarly, which means we are taking complement for 2 times, which meant that you are getting the same output equation. Okay, and if you consider the next case, see here it is A B bar, and if you feel confused, you can directly draw the logic diagram for A equal to B, A greater than B and A less than B. So this is with the help of your universal gates NAND and NOR. Hence it is A, so this is for only A B bar, is it? So this is A B bar to the whole bar, is it? And once again if you give, see these and all, it is an inversion operation for A is equal to B, hence you are getting it as A exclusive NOR B, A exclusive NOR B to the whole bar. Okay, this is an 1-bit magnitude comparator. And if you see, if you go for 4-bit magnitude comparator, the condition for A greater than B can be possible in the following 4 cases. Let us say your A is of 4-bit, which is of A3, A2, A1 and A0, and B is of 4-bit, B3, B2, B1 and B0. And in this case, if A3 is equal to 1 and B3 is equal to 0, that is one condition in which A greater than B. And if A3 and B3 are is equal to, say, both are same, and A2 is equal to 1 and B2 is equal to 0, in that condition A greater than B. Similarly, if A3 is equal to B3 and A2 is equal to B2, both the bits, see here, if both the bits of A3 and A2 are equivalent to B3 and B2, the next condition we need to check is A1 greater than B1. Is it? If both are equal, see, if both are equal, we need to check whether your A1 is greater than B1. If that is the case, see, that is what it is given here. If A3 equal to B3 and A2 equal to B2 and A1 is equal to 1 and B1 is equal to 0. If this is the case, we identify that A is greater than B. Similarly, for the other three bits that are equal, if A3, A2, A1, all the three bits, and B3, B2, B1, all the three bits are equal, and if A0 is 1 and B0 is 0, once again the condition is A greater than B. For all these conditions, if we refer, see here A3, B3 bar, and the next case is A2, B2 bar. Is it? We can also add for A3 equal to B3. If you add, that gives another equations, and you can implement that logic equation also. See, the output of A3, B3 bar is considered as X3, and X3 can be given here. And that is also in another case where you can write the equation. This is another equation where you can write for A greater than B. And if once this condition is over, and if A2 and B2 bar is there, so that is also the condition where A greater than B. And next case is A1, AB1 bar, and next case is A0, B0 bar. This is the condition to check A is greater than B. Similarly, the condition for A less than B can be possible in following four cases. So once again, we are considering the same four bits for A and B. Is it? And if A3 is equal to 0 and B3 is equal to 1, previously we are considering A3 equal to 1 and B3 equal to 0 for greater. Here we are considering A3, if it is 0 and B3 is 1, A3 is less than B. Is it? Hence, we are writing it as here A3 bar B3. Okay, similarly, if A3 and B3 are equal, see, if A3 and B3 are equal, next we need to check whether A2 is less than B2. So if we need A2 is less than B2, which meant that this should be 0 and this should be 1. Is it? So that is what it is given here. A3 equal to B3, and if A2 is equal to 0 and B2 is equal to 1, the condition is A less than B. And you see then another two bits, if A3 equal to B3 and A2 equal to B2, and if A1 is equal to 0 and B1 equal to 1, the condition is A less than B. And similarly, if A3 equal to B3 and A3 equal to A2 and A1 equal to B1 and A0 is equal to 0 and B0 equal to 1, the condition is A less than B. So that is what it is given here as A0 bar B0. For the third case, it is given here as A1 bar B1, and for the second case, it is given here as A2 bar B2. Similarly, here it is A3 bar B3. Now we have framed the equation, and if you go for the condition A equal to 1 is possible only when all the individual bits of one number exactly coincide with the other bits of the corresponding bits of another. Is it? So in that case, we are writing it as A3 XOR B3, A2 XOR B2, A1 XOR B1, A0 XOR B0. If the conditions are equal, the XOR condition is performed between two bits. So that is what it is given in this figure, in this logic diagram. See, it is for A greater than B. We already find the equation A greater than B. It is A3 B3 bar. Is it? So that is what it is given in this logic diagram. See, it is A3 bar. The 3 B3 bar. Is it? Similarly for A2 B2 bar. Is it? And then similarly for A1 B1 bar, and similarly A0 B0 bar. All these are given to the OR gate to identify whether your A is greater than B. Similarly, we are draw the logic diagram for A less than B, and similarly we are draw the logic diagram for A equal to B. For A equal to B, exclusive OR is performed between the bit operations of A0 B0, A1 B1, A2 B2 and A3 B3. This is the cases. Okay. So similarly for n bit comparator we can identify n bits or we can choose n bits and we can frame this logic equation and we can draw the logic diagram. Thank you. I hope this video helps you to understand the n-bit comparator. So initially we have started with a 1-bit comparator and we have 1 to 4-bit comparator. Similarly for any 8 bits or for 32 bits or for n bits it can be done.